Hello and welcome to this second video presentation on nodal analysis. So in the first video we kind of went over an overview of what nodal analysis was and what it was we were solving for. And we found out that what we are solving for when we do nodal analysis is we are solving for these different voltages, the voltages that the different nodes in the circuit are at. So what we're going to do in this video is we're going to do an actual example of nodal analysis. And hopefully you'll see from this example sort of how nodal analysis sort of works. So I'm just going to go ahead and erase that kind of example circuit. And we're actually going to start with a circuit that maybe it's not that complex, but it's not that easy either. We're going to start with a circuit that looks like, say I've got a resistor, and I'm actually going to put in values here. Let's say I've got a 5 ohm resistor here. Let's say I've got, 7 ohms here. Let's say I've got a current source that's putting out, let's say 2 amps. 2 amps going that direction. And I'm going to tie all this together. Let's say I've got another resistor here that's giving me 9 ohms. And then let's say I've got actually here, let me put a current source here that's pushing, 7 amps of current in that direction. So what we are going to do is we're going to analyze this circuit using nodal analysis, and what the information I want out of this circuit right now, I'm actually going to say I want 2 things out of this circuit. We're going to use nodal analysis to get both of these things. I want to know what is this V out right here. So I'm going to call this voltage difference my V out. So what is that V out? I'm going to call that plus minus. Actually, you know what? Instead of V out, I'm just going to call that V0. What's my V0 here? And I also want to know what is, let me get a better color, what is the current through this 7 ohm resistor. And specifically, I'm looking for the current that's going kind of top to bottom here. I want the current that starts here and flows top to bottom through that resistor. And I'm going to call that I0. So those are the 2 things I want for this circuit. So what we're going to do, and we are going to do this every single time we do nodal analysis. Essentially, the big equation that matters when we do nodal analysis is that the current that goes into a node is going to be equal the current that flows out of the node. So you can kind of think of this as sort of like if I have a hose and there's a junction in the hose, and say, 5 gallons of water flows in one part of the hose, then we have to have 5 gallons of water that flows out of the hose. Or maybe it would probably be better if we said like 5 gallons per minute flowed into one section of the hose. Then that means that if we summed up all the water that flowed out of the hose, and maybe we split that hose into a bunch of different sections, but if we were to sum up all of those different flows of water out of the hose, if I am providing 5 gallons per minute into the hose, then I've got to get out of the hose 5 gallons per minute. I can't, it's not like water is accumulating anywhere in a hose, like if I just have a typical garden hose. The flow that I put into the hose has to equal the flow that I get out of the hose. And that's exactly the way it pretty much works in a typical circuit. Now, I should say that we are assuming in these circuits that we're drawing, and it's a pretty valid assumption, that we're not going to have like charge build up at any point inside of one of these nodes. If we had a buildup of charge somewhere, then we couldn't say that what came in equals what goes out, because we could be building up charge here. And that typically that doesn't necessarily happen in a circuit. When that does happen, it means that you've got some amount of a capacitance, which we will talk about in future videos. And you'll definitely learn about it more as you progress in any circuits class that you're taking. if we assume that we're not going to be building up any charge, then the current in, and I'm actually going to say the current, my I that goes in, so I sub in, you can think about that. So the current that goes into a node equals the current that flows out of a node. So now I've got this circuit up here, and let me actually just color in that one purple thing I've got. So I've got this circuit up here, and the first thing I want you to think about is just how many nodes do I have in this circuit, okay? And remember that a node is pretty much, it's essentially, I guess, a wire in this diagram. It's a point where everywhere on the wire, everywhere on the node, the voltage is going to be equal. So if I look at this, I can see that I have got this whole thing up here. Let me color this in. So this whole part of the circuit is one node. So this whole part of the circuit is one node. And it is going to be at some voltage. And let's even, actually let's call that, yeah, let's just go ahead and call that V0, right? Because if I say I'm going to ground this end of the circuit. So if I ground this end of the circuit, that means that I've got another node here. Let me color in this whole node. So I've got another node here that is kind of everywhere on the bottom, this entire node, and that I0 arrow is part of the node. So I've got this entire node on the bottom. And if I set this node to ground, if I ground that side of the node, then this entire node is going to be at 0 volts. So it's sort of like, you know, in order to solve for my V0, what I really care about is voltage difference between two parts of a circuit. So if I want to be able to solve for what this V out is, I'm going to have to say what this voltage is on the bottom. Hopefully you've seen this before. Hopefully this isn't new. That if I ground this side of the circuit, I am going to be saying that this entire node, this node on the bottom, is going to be at 0 volts. Now typically, or I shouldn't say typically, when we do nodal analysis, if we have two nodes in a circuit, or when we do nodal analysis, we will write one fewer equations than the number of nodes in a circuit that we have. And typically what that means is we will write an equation for every node except for the ground node. So essentially we'll sum up all of the different currents, what goes into a node equals what goes out of the node. We will do that for every single node in a circuit except for our ground node. So let's go ahead and do that. We are going to essentially do that. We're going to write the current in equals the current out, and we are going to do that for our V0 node. So now one last thing, actually I should say, one last thing we need to do before we start writing this equation is we are going to actually label current. We are going to name different currents that go through these resistors. And we are also just going to assume directions. I'm going to draw these different currents. So right now I've got I0. I'm just going to keep that the same. I'm going to call the current that flows from top to bottom through this resistor. I'm going to call that I0. And then this 5 ohm resistor, I'm just going to randomly say, let's call the current that flows from the bottom to the top through that 5 ohm resistor. And I'm just assuming a current direction. I could assume a current direction in any direction I want. Right now for this 5 ohm resistor, I'm going to say current's going to flow from the bottom to the top. And I'm just going to call that current, I'm going to call that current I1. And then what we've got over here is we've got a 9 ohm resistor. And let's just say that, on this 9 ohm resistor, current is going to flow from the top to the bottom, and I am going to call that current. I'm going to call that current I2. So now I've named all of the currents, and I've assumed a current direction through all of the resistors. And again, I can assume whatever direction I want, and still my nodal analysis is going to work out. And the other currents here, I've got a current source here and a current source here, but those currents are already known. I know what those currents are. So I don't even really, I could name them if I want, but like if I was going to name this, like say I named this current I3, I already know I3 is equal to 2 amps. Let's say I named this current over here I4. Notice that it's the current that's flowing from the bottom to the top. What would this, if I4 flows from the bottom to the top, notice that I4 would be equal to negative 7 amps here because it's flowing the opposite direction of the way my current source is kind of pushing current. So, but anyway, we don't really need to define I3 and I4 here for our current sources because we already know what those currents are. Those are like definite numbers, so we don't really have to name them something else. So I'm actually just going to get rid of those, that I3 and I4. And now with this information, let's just go ahead, and maybe this is a good idea for you to try to pause the video right here, or else actually, you know what, I'm going, yeah, good idea to pause the video right here and try to write this equation for yourself. Try to write the current that goes into our V0 node is going to be equal to the current that flows out of our I0 node. So pause the video and try to do that. And now I'm going to assume that you've, I guess, unpaused the video. And I'm going ahead and I'm going to do that. So the currents that flow in, so I'm going to concentrate on the currents that flow in first. So I've got this 7 amp that is flowing out of my V0 node. So I'm going to deal with that when I deal with my outward currents. I've got this current that's also flowing from top to bottom, so it's flowing out of my node V0. And then over here I've got 2 amps that is flowing into my node V0. So I'm going to go ahead and write this 2 amps on the left-hand side of my equation because it's flowing into my node V0. So 2, and I'm going to go ahead and leave the A off. I'm just going to call that 2 for 2 amps. Now I've got this next one, this I0 current that's flowing from the top to the bottom. And so that one's also flowing out. And then I've got my current I1. That's flowing in. So I'm going to say that the current that flows in to V0 is going to be 2 amps plus this current I1. So 2 plus the current I1. So now I'm going to go ahead and do the same thing for all the currents that are flowing out of my node V0. So I start over here again. I've got the 7 amps that's flowing from top to bottom, so that's flowing out of V0. So I'm going to say that this is going to be equal to the 7 amps flowing out, so that is 7. I'm just going to write it as 7. I'm going to assume that this entire quantity here is going to be in amps, so I'm just going to leave off the A, so just 7. I2 also flows out. It flows from top to bottom, so I'm going to add on I2. 2 amps flows in, and we already took care of that. And now I0 also flows out. I0 flows from the top to the bottom. So I'm going to say plus I0 because I0 is flowing out. And then I1 flows into the node V0, and we already took care of it over here. So this is kind of the first stepping stone in doing nodal analysis. We've written our kind of the big equation for nodal analysis, that the current that goes into our node V0 equals the current that goes out of our node V0. I'm approaching the 15-minute time mark on this video, so I'm going to actually stop it here. And in the next video, we're going to talk about how we deal with this expression that we've gotten. Because remember, what we want to get is we want to figure out what our I0 is. And before we can figure out what our I0 is, what we always solve for in these nodal analysis problems is we always solve for the unknown voltage, the voltage we don't know. So thanks for watching, and I will see you in the next video where we will hopefully finish this example. Thanks for watching.